But in the future when you learn protocols like BGP, you'll see wildcards again. So now let's just understand. Let's briefly talk about this 254. For 254. The last one it is 1.0. After 1.0 this is a 254. It means that here are 7 ones and 1 0. Then the rear is a 0. Then below this is 0. Represents that the last digit is fixed. Only this is a 254. The last bit in 254 is 0. Then it is actually 0001. So when we go to match, it is equivalent to matching all even numbers in this interval. Look at the 254 just now. It's just the last one. Now this 254 is placed in the middle. This is a 1. Is 00000001. It is 11111110. Represents that except the last one is 1. Everything else is arbitrary. I also said, it will match all odd numbers in the interval in this range. Because the last bit has a value of 1. No matter how you add it to the front. The front is mutable. No matter how it changes. It is an odd number. It is equivalent to if we use this form. 192.168.1.0. Its wildcard is like this. It is equivalent to this 192.168.x.0 that it matches. X is any number. That is, all odd-numbered network segments. For example, 192.168.1.0, 3.0, 5.0, 7.0 etc. So we call the wildcard a jumping inverse mask. You may find it difficult to listen. You can watch the video several times after class. You need to know what it means. Here's what we're talking about: masks and wildcards. Actually, our ACL is finished. If for basic ACL configuration, you want to match the previous network segment, dedicated to killing a network segment, you can try to configure it yourself after class. The command is like this. Enter a matching IP address. Add a wildcard after the IP address. Usually, if it is a 24-bit network segment, followed by 30 and a 255 on the line. Under the adaptation range of a relatively regular network segment. It actually looks the same as the anti-mask. Unless you have special needs in the future. You have to use wildcards again to calculate. At this stage, you can understand it as an anti-mask. Okay. Above this is the ACL. Let's talk about the next experiment. We are going to learn NAT. For NAT, we will configure while teaching. I turn it off first. Let's start the next experiment. I have to open it first. Otherwise, it will be a little slow to load in a while. This is an experiment with NAT. Like ACL and NAT. Actually they are very simple. It's for experimentation. First, let's talk about the NAT scenario. So let's discuss a question. It is known. The address we are using now is an IPv4 address. Now the overall network environment uses IPv4. Remember how many IPv4 addresses there are in the world? When we talked about IP addresses before. A total of 32 bits. Each bit has two values 0 and 1. That is 2 to the 32nd power. About 4.29 billion addresses. Less than 4.3 billion. The world now communicates using IP addresses. As long as the device wants to connect to the internet. Must have an address. That is, now all devices that can be controlled through the network. It will have an IP address. For the world, 4.3 billion addresses are not enough. We said it before. We will use private network addresses internally. and run the public network address on the public network. Then everyone will have heard a sentence. The private network address cannot run on the public network. The public network does not forward the traffic of the private network IP address. Why doesn't it forward it? For example, 192.168. This is a standard C-class private address range. An address like this, since it is a private address, it means that we can use, whether at work or at home, even a small restaurant outside, for such an address that everyone can use. If someone sends a data in the future, go to 192.168.1.1. The data reaches the carrier's device. If it can really help you retweet. So where is this address? For the whole world. Use an address segment like 192. So many private addresses. It does not know which 1.1 you are going to. So it will not help you with data forwarding. That is, because the addresses of these hosts in our internal private network has too much overlap. So when the operator forwards, it will appear confusing. So it can't help you retweet, since it can't be forwarded. How do I get online now? We are now deploying a technology on export called NAT, Network Address Translation. It is possible to convert between addresses. That is, when we are sending data, we're going to convert the data to it. We modify the original address of the data. Then we can convert the private network address into a public network address. Form a local mapping information. Then I can send data. Then if the future data is returned, when I receive data, will be based on the current destination address in this local mapping information table, to see if there is this record. If so, then we convert the address back to, that is, change this destination address to a source IP of the private network in the NAT table. This is the idea of NAT. Modify the source address of the data when sending. Change to a public network address. Form a message locally and send it out. When receiving data in the future, send it to this public address. Then I check in the local mapping table. Is there a private network address converted to this public network just now? If there is, I will change the current destination address to the original source IP address of this private network. Send this data again. It might be more abstract. Let's look directly at this picture. This is a public network. Here is a 200 network segment. This is a public address. We use a private network address internally. In the future, when host A is surfing the internet, I would pass such a device here. When the data is sent out, a mapping relationship will be formed locally. For example, 192.168.1.1. It is now mapped to 200.10.10.1. Let's say this is its address. So now after forming the mapping relationship, this data will be sent out. This is the source IP. When a server on the public network receives reply packet to data, reply packet words, swap source IP and destination IP, it replies to this public address. Then this data will be replied to this interface of this device. Since this data is not sent by this router, it has to be viewed locally. Did someone just go online with such an address? If so, let's see who uses it. Is 192.168.1.1 used? Then the original destination IP in this data is 200. Is its interface. It now modifies the destination IP. Then send back. So equivalent to. Host A uses a private network to communicate with a public network. So this is how we go online now. NAT is generally deployed on a network connected to the internet. This is a base location where we deploy There are 4 modes in NAT. Let's talk one by one. Make a configuration for each talk. The amount of configuration is still quite large. Let's take a look. The first is static NAT. When we configure, there are many ways to implement NAT. Static NAT is one-to-one between private network address and public network address. One-to-one is: I have several hosts with private IP. There must be several public network IP addresses for it to map. Do you think this method is useful? You said that a private network IP is converted to a public network IP. Then communicate with a public network. Another private network. You have to use another public network address to communicate with the public network. Then why don't I directly use this public network address to communicate with the public network? This is static NAT. Of course, static NAT also has some security risks. But let's not talk so much, because now it's useless. Let's just talk about how it's done. As a static NAT, this is a translation source address. Now host A sends a data to send to host C on the public network. This is the source IP and destination IP. Then after doing static NAT on the gateway, it will forward a corresponding. Then when retweeting, everyone will find the destination IP is unchanged.